This summer, I studied embedded V-defects, or V-pits, in a commercial green LED by examining how current injection and electroluminescence varied across the device. Green LEDs are much less efficient than blue LEDs, and understanding these defects could help explain why. In an LED, applied voltage causes electrons and holes to recombine in quantum wells and emit photons as light. Indium gallium nitride LEDs can naturally produce efficient blue light, but shifting the emission to green requires increasing the quantum well's indium concentration, which unfortunately reduces efficiency. Many efficient green LEDs contain intentionally grown cone-shaped defects called V-pits. Their rims contain less indium than the surrounding flat regions, allowing current injected into the rims to laterally transport into the high indium regions and produce green light more efficiently. To study this process, we use a scanning tunneling microscope. Its tip converges to a single atom, allowing us to electrically probe the sample and measure the light emission on the nanometer scale. In my sample, the V-pits were buried beneath a p-type gallium nitride layer, making them difficult to locate. After learning how to operate the STM, I identified the V-pits in the topography and used them as reference points for my measurements. I then set up a 32 by 32 point measurement grid on the STM. At each point, I swept the voltage from -10 to -2 volts while simultaneously measuring tunneling current and emitted photon intensity as a function of voltage. I analyzed these measurements in Python to create maps showing how current injection and light emission varied across the sample. The maps showed that current was injected more easily into the V-pit rims, which also produced significantly more light, while the centers showed almost no current or light emission. These measurements allowed us to electrically identify embedded V-pits in an operational commercial LED without modifying the device. They also improve our understanding of how V-pits enhance green LED efficiency, bringing us closer to more efficient white light produced from red, green, and blue LEDs. I'd like to thank Dr. Alastair Rowe, Dr. Natalia Alyobieva, Christian Robert, and the staff at PMC for teaching me so much this summer, as well as Dr. Stevie Alisov, everyone at the University of Michigan, and the NSF for making this opportunity possible.